Hello and welcome to yet another vector video. Consider triangle OAB with length of OA equals 2 and length of OB equals 3 and angle AOB equals pi over 3. Let H be the foot of the perpendicular from vertex O to side AB. Then what would be the ratio of the length of AH to the length of HB? So this is a rather simple geometry problem, and you can solve it with either classical geometry or by using coordinates if you want to. But since I've been making vector videos recently, I am going to present you the third method, the vector method. And the gist of this method is like this. Let vector OA as vector small a and vector OB as vector small b. And consider this vector OH. Then all we have to do is to express this vector OH in terms of vectors A and B. That is, vector OH expressed as C1 vector A plus C2 vector B, where C1 and C2 are constants. And now is the good time to ask this question. Why? How does this method work? Why would expressing vector OH with vectors A and B give the answer AH to HB? Here I am going to solve this problem using vectors, and in the process I will explain some basic but important properties of vectors that can be quite handy when solving problems like this. First of all, solving the given problem requires one important lemma, which I am going to explain now. Consider line segment AB and suppose that H is an arbitrary point on that line segment. Now, if we take a reference point, such as this point O, which can be origin of the xy plane or other convenient point depending on the situation, then we can express these points as position vectors OA, OB, and OH. This is quite important concept, you know. Vectors are another means to express points. The lemma is, if point H is on the line segment AB, then vector OH can be expressed as t times vector OA plus 1 minus t times vector OB, where this t is a real number from 0 to 1. Or if we denote two endpoints as simply vectors A and B, then OH equals TA plus 1 minus TB. That is, vector OH can be expressed as a linear combination of two endpoint vectors A and B, and the sum of their coefficients must be 1. Moreover, this expression also gives the information of ratio AH to HB, which is 1 minus T to T. Okay, this is quite an interesting property, but it is also the right moment to ask, why? Why does this lemma hold? Why does the sum of coefficients becomes 1? Well, in order to prove this lemma, we have to learn one more thing about vectors, which I have not mentioned in my previous vector videos, and that is vector subtraction. Yeah, we need to learn how to subtract vectors. If you already know how to do so, you can just skip this section, but in case you do not know, I am going to explain how it works. First, let's start from something you might already know, something that I have already explained before, vector addition. We know that if we add vectors AB and BC, we obtain vector AC. Now from here, let us move this vector AB to the right hand side. Then it must have minus sign, so we obtain vector BC equals vector AC minus vector AB. And this is the basic principle of vector subtraction. In terms of position vectors, it looks like this. Let us consider two position vectors OA and OB using this O as a reference point. Then, if we do the subtraction OB minus OA, we obtain vector AB. That is, the result of this subtraction is a vector from the head of the second vector to the head of the first vector. If you're curious, you can draw this opposite vector minus OA and do the vector addition to verify. Now, this knowledge gives you additional method to split the given vector, this time into difference between two vectors. Consider a given vector AB. Then we can take an arbitrary point C and split this vector AB into vector CB minus vector CA. Okay, now with this knowledge, we are ready to prove the lemma. Here, suppose that the ratio of AH to HB is 1 minus T to T. Then we want to show that vector OH is expressed as T times OA plus 1 minus T times OB. First, let us consider two vectors, HB and AB. these two vectors are parallel, so vector HB can be expressed as a scalar multiple of vector AB. More specifically, since AH to HB is 1 minus T to T, the ratio of HB to AB is T to 1. Therefore, vector HB is T times vector AB. Now it's time to use vector splitting, but with subtraction. You see, using this reference point O, vector HB can be expressed as vector OB minus vector OH, and vector AB can be expressed as vector OB minus vector OA. So we have vector OB minus vector OH equals T times vector OB minus T times vector OA, and if we solve for vector OH, we obtain T times vector OA plus 1 minus T times vector OB. Hence, we have proved the lemma. We are definitely going to use this lemma when solving the given problem, but we still require one more property regarding vectors, and that is the dot product. Now, some of you may already know about the dot product, and if you do know, you can just skip this entire section. For the rest of you, I will briefly explain what the dot product is. Consider two vectors A and B, where this theta is the angle between these two vectors. Then, the dot product of A and B can be calculated as the norm of vector A, which basically means magnitude of vector A, times the norm of vector B, times cosine theta. So this is the dot product, which gives scalar value as its result. And although I am not going to prove them, this dot product has some basic properties that are somewhat similar to operation between scalars, such as commutative, distributive, and this property about the multiplication of scalar k. But the most important property related to dot product is perhaps this. There's this cosine theta term in the dot product, which becomes 0 when theta becomes the right angle. This means that if two vectors are perpendicular or orthogonal, which is just more general term of perpendicular, then their dot product is simply 0. Alright, now with the dot product covered, we are really ready to solve the main problem, so let's get right on to it. Solution to the main problem. So first, this H is a point on the side AB, so by the lemma, vector OH can be expressed as T times vector OA plus 1 minus T times vector OB, where T is a real number between 0 and 1. Next comes the property related to this perpendicularity. Since vectors OH and AB are perpendicular, their dot product must be 0. Here, vector AB can be split into vector OB minus vector OA, which is vector small b minus small a. Next, using this expression for vector OH, we have T times vector A plus 1 minus T times vector B dot vector B minus vector A equals 0. We can expand this using the distributive law similar to the multiplication between scalars. So from here, we have T times A dot B, and from here, we have minus T A dot A, and from here, we have 1 minus T B dot B, and from here, we have minus 1 minus T A dot B. First, let's take a look at this. The angle between two identical vectors are of course 0, so this A dot A simply gives norm of the A squared. Similarly, B dot B is norm of vector B squared, so we have minus T norm of vector A squared plus 1 minus T norm of vector B squared, and the sum of this term and this term gives 2t minus 1 A dot B equals 0. Here, norm of vector A is 2 and norm of vector B is 3. Therefore, its squares are 4 and 9. So we have minus 4t plus 9, 1 minus t plus 2t minus 1. A dot B equals 0. Here, this A dot B can be obtained by the definition of dot product, which is this. So 2 times 3 times cosine pi over 3, which is 3. So this part is 3. So we have Minus 4t plus 9 times 1 minus t plus 3 times 2t minus 1 equals 0. And if we simplify, we have minus 7t plus 6 equals 0, which gives t equals 6 over 7, which is indeed between 0 and 1. This value of t gives vector OH equals 6/7 vector A plus 1/7 vector B. And this means that the ratio of AH to HB is given as 1 minus t to t, so it should be 1 to 6. Alright, so we have solved the problem, but some of you might want to ask one final question. Why? Why do we have to learn about vectors and dot products and use this seemingly complicated method when it can be solved by simple basic geometry or using coordinates? Well, first of all, this method does not involve the Pythagorean theorem or distance between 2 points, which is essentially the Pythagorean theorem or law of cosines or any other laws that involve square roots. So that can be considered as simplicity. But the main thing I want to say here is, although these new properties and operation look more complicated at first sight, if you understand them and get used to them, it might come quite handy in certain situations, especially when you're doing geometry in coordinate plane or even in coordinate space. I would really like to tackle those in my future videos, but for now, this is the end of my video. So thank you for watching, and I will see you in another video.